Welcome back. We are beginning week 6 but continue to work with logic based testing. Just to recap logic based testing, we saw basics of logic, these various logic coverage criteria as you see in this slide. Predicates and clauses constitute the logical expressions that you find in decision statements. And we could just test for the predicate being true or false, which is predicate coverage, exercise each clause to be true or false, which is clause coverage. Then if we test how a clause influences a predicate, then you get active clause coverage, 3 variants: general, correlated and restricted. If we test how a clause does not influence a predicate, then we get inactive clause coverage, and all combinations coverage exists theoretically to test for all possible combinations of truth values, typically infeasible. We saw these coverage criteria, and at the end of last week I told you about one example of a thermostat, about testing the code or the decision points in that statement with logical expressions. What we will do this week is to see a few more examples. This lecture will look at one more example with logical expressions in code, and moving on we'll see specifications, logical expressions in finite state machines and so on. So as I told you last week we saw a thermostat, and now I'm going to take another program which you will find commonly in several books on software testing and books on software engineering that deal with chapters in software testing, which is to detect a type of a triangle. And this program typically tends to have interesting combinations of logical expressions which we can test for. So all of us know how to test what type of a triangle, what type a given triangle is. Triangle has 3 sides, and if none of the 3 sides have equal length, then we say it's scalene. Isosceles is if 2 sides are equal. Equilateral is all 3 sides are equal. Sometimes your program might get inputs where the thing is not a valid triangle also. So this program basically takes the 3 sides of a triangle and tests for properties by which it can conclude whether the triangle is scalene, isosceles, equilateral or not a valid triangle. So this is a program which has a class called try-type, type of a triangle, and as I told you, it tests whether the triangle is scalene, isosceles, equilateral or it's not a valid triangle. Takes 3 inputs A, B and C corresponding to the 3 sides of the triangle. Then it also has T, which we will see, and first it takes the inputs here in lines 7 to 13, where it says enter first side, enter second side, enter third side, and then calls this method called triang with the 3 sides A, B, C as input. The triang returns a variable which is written onto T, and based on T it says what the sides are. So this is the main triangle classification method called triang. The inputs A, B and C here are passed as side 1, side 2 and side 3. So if you remember in call graphs, this line number 14, the method triangle is called with inputs A, B and C, which are coupled to side 1, side 2 and side 3 in line 16 at this call. Now this method triangle basically takes these inputs and based on their property decides whether it is a particular kind of triangle or not. So it outputs a variable called tryout, and tryout has this values as a convention. If tryout is 1, then we say triangle is scalene. If tryout is 2, then we say triangle is isosceles. If tryout is 3, then we say triangle is equilateral. If tryout happens to be 4, then we say it's not a valid triangle. We'll see how these values for tryout are populated in the code. So the code runs over a few slides, this slide, next one and next one. So I'll walk you through that first. So first, I hope the values for tryout are clear. 1, 2, 3, 4 represent each kind of triangle: scalene, isosceles, equilateral and not a valid triangle. First line number 18. If side 1, side 2 or side 3, any of them are values less than 0 or equal to 0, then you say the tryout is 4, which means it's not a valid triangle, and return it. So that's an easy check to do. Now you have to check whether two sides are equal, then it's isosceles, all three sides are equal, then it's equilateral. The same check is being done in a slightly long fashion here, just so that we have a lot more predicates to reason about while doing logic based testing. So don't worry about whether this is the most succinct, easiest way of checking for type of a triangle. It may not be, but the code works correctly in the sense that it does check whether the triangle is scalene, isosceles or equilateral, and populates values for tryout as 1, 2 or 3 respectively. So after this check here about the triangle not being valid, it goes here, sets the value tryout to 0, and based on two sides being equal at a time, it goes on incrementing the values of tryout. So it says if first check set tryout to 0, check if side 1 is equal to side 2, if it is, increment the value of tryout by 1. If side 1 is also equal to side 3 in line 24, increment the value of tryout by 2. If side 1 equal to side 3, then increment the value of tryout by 3. If tryout equal to 0, then you check whether this is true, properties of the triangle, right? Sum of two sides should be less than or equal to, greater than or equal to the third side. But if that is not true, then you say side 1, if side 1 plus side 2 is less than or equal to side 3, or side 2 plus side 3 is less than or equal to side 1, or side 1 plus side 3 is less than or equal to side 2, confirm that is not a valid triangle by setting tryout to be 4, otherwise return tryout to be 1 and return this value. So you can run a few sample triangles through this to check whether it is true or not. Now it says if tryout is greater than 3, reset it to 3, otherwise you check whether if tryout equal to 1 and if side 1 plus side 2 is greater than side 3, then you say it's isosceles, else if tryout equal to 2 and side 1 plus side 3 is greater than side 2, then you say it's isosceles again. Or if tryout equal to 3 and side 1 plus side 2 plus side 3 is greater than side 1, then you set it to 2, which is isosceles again, otherwise you say it's not a valid triangle. So between these three slides, what is happening is it takes these inputs A, B, C, passes it to sides 1, 2, sides 1, 2 and 3, and does a slightly longish kind of code to check whether it's a valid triangle or not. Here it confirms that it's not a valid triangle in 18 and 19. And this code here that you see in the second slide, lines 21 to 32, followed by 33 to 42, basically is a slightly long procedure to correctly input the classification of the triangle to be isosceles, equilateral or scalene. Now if you see, our goal was to take this as an example to understand how logic coverage criteria is applied to testing. And it seems like a useful example because if you see, this code is filled with predicates. At line 18 there is this predicate which has 3 clauses. At line 22 there's a predicate 24, 26, 28, 29, 33, 35, 37, 39, all these are predicates. So there's so much to test for. So this program basically, as I told you, has 3 inputs read into variables A, B and C, passed to side 1, side 2, side 3 in the triangle. We have one more point. If you see this method triang here has an internal variable called 17, at line 17 called tryout. This tryout is what is passed back as T. So this internal variable, the predicates, if you see side 1, side 2, side 3 are in terms of the coupled variables. This is again in terms of coupled variables. This is again, but these predicates here, 33, 35, 37 and 39 involve a local variable called tryout. So we have to solve for tryout because tryout is an internal variable, and we have to also solve for reachability of various predicates. We'll do it manually for now. So I'm just listing out here all the predicates that you see in that code. We saw this earlier. Line 22 there was this predicate, line 18 there was the large predicate which checked whether the triangle was invalid or not. Then 22, 24, 26, 28. Line 29 there was predicates. Line 33, 35, 37 and 39, which was in the last slide, involved this local variable tryout. So totally this slide basically pulls out the predicates from the code and lists it here. Now let's see. in all these predicates, I have to work out RIPR criteria. How can I reach that particular statement? If that particular statement has internal variables, how do I rewrite it in terms of inputs? Because my test cases are going to be in terms of inputs. And if there is an error or something like that, how do I propagate? So let's first work out conditions for reachability. Line 18 is one of the first predicates that you find in the code. So it's always reachable. So reachability condition for line 18 is true. At line 22, it's an if statement which came because line 18 was not true. So line 22 says side 1 will be greater than 0 and side 2 will be greater than 0 and side 3 will be greater than 0. Why? Because line 22 was basically going, you could go to line 22 if line 18 would return false. Line 18 says one of these slides is less than or equal to 0. So line 22 is the opposite of that. Because just to fit it into one slide, I have abbreviated side 1 as S1, side 2 as S2 and side 3 as S3. Please remember that there's this piece written here. Similarly, for lines after 22, lines 24, 26 and 28 are immediately reachable. So this reachability condition P1 is true for lines 24, 26 and 28 also. Line 29, maybe we'll go to the code for a minute to see what line 29 is. That's this line. So that is, I've done with 22, 24, 26, 28. Now I've come to 29, which is this condition. Sum of two sides being less than or equal to the third side combined with an OR. Right. So for line 29, I basically write out the conditions. So it says P1, which was for lines 24, 26 and 28, plus tryout value should be equal to 0. So let's go back and check that. It should be correct. Line 29 is reached if 28 becomes true. 28 becomes true if tryout is 0, and then these conditions. Is this clear? So that's what is reachability for line 29. Now the else of line 29 is the negation of that, so P1 and the opposite of that. I'm just continuing to list the reachability conditions for the predicates in the other lines 33, 35, 37, 39 and the else part of 39. It's basically all these lines that you see here. 33 is tryout equal to 3, tryout is greater than 3, 35 is this else if, 37 is this else if, 39 is this else if and so on. I have to solve for tryout, but I have not yet done that. I have just listed the conditions here for reaching. Now I'll solve for tryout. Specific lines here had specific values for tryout. So let me just go back to the code. So 33 says tryout was greater than 3. 35 says tryout is 1, 37 says tryout is 2, 39 says tryout is 3. So I'll solve for specific values of tryout. So tryout will be 0 precisely when S1, S2, S3, remember, are short forms for side 1, side 2, side 3. Precisely when S1 and S2 are not equal, S1 and S3 are not equal, and S2 and S3 are also not equal. Similarly, tryout will be 1 if S1 and S2 are equal, but the other two are not equal. Tryout is 2 if the center part S1 is equal to S3, but the other two are not equal. Tryout is 3 if S2 equal to S3, but the other two are not equal. All combinations like that. For 4, 5 and 6, 2 of them should be equal, 1 should not be equal. 2 of the 3 sides should be equal, one side should be unequal. So this is the rules that let tryout take values as 0, 1, 2, 3 and so on up to 6. Now after solving for tryout, so if you remember here I had tryout not equal to 0, tryout not equal to 0 and tryout less than or equal to 3 in my reachability condition, right? So now these are my values. So I have to substitute them back because I have to write all the predicates purely in terms of inputs, because that's when I can pass them as test cases. So now I do reachability for predicates after solving for the variable tryout. At line 29, I have P1, which was that shortened form, and this part. The else of line 29, I am just substituting for tryout here. The else for line 29 is again P1 and the substituting value for tryout. Line 33, I again substitute for tryout. I use this table to substitute for tryout and so on. I am not listing all of them, but basically what I have done is, let me just go back for the sake of completeness. I took the code. First we listed all the predicates in the code. That's what is this slide here. This slide basically lists all the predicates with their line numbers. Some predicates directly had variables that were coupled to inputs, which is side 1, side 2, side 3. So we could directly pass test cases to them. Some predicates like the one in line 28, 33 and all had the internal variable tryout, where we couldn't directly pass input. What we did was we wrote the reachability conditions for all the predicates. Then we said, let me take the internal variable tryout and rewrite it in terms of the values of the variables, input variables that I have. That's this table. Now the reachability conditions, wherever tryout was involved, that is these predicates, lines 29, else of lines 29, 33, 35 and so on, all these predicates had the variable tryout, which could be rewritten as inputs like this. I substituted back. The formulas will just get longer and longer, but nothing goes wrong. You can, the nice thing is that all the predicates now have been found to be reachable. I know the conditions for their reachability purely in terms of values of the inputs, right? So now I can look at various logic coverage criteria: predicate coverage, clause coverage, correlated active clause coverage, general active clause coverage. Any kind of coverage criteria I can do. Let's see a few as a sample. So let's say I want to do predicate coverage for predicates. In this table I've taken 4 of the predicates, the ones that occur at lines 18, 22, 24 and 29. So these are the predicates. Again, please remember S1, S2 and S3 are short forms for side 1, side 2 and side 3. How do you read this table? These set of values, inputs were A, B and C, which were coupled and passed to side 1, side 2 and side 3. EO stands for expected output. So if I give inputs as A, B, C as values 0, 0 and 0, the expected output is it's not a valid triangle, which means the variable tryout should take the value 4. That's what is given here. Is it clear? For predicate coverage to be false, I could give any set of values for A, B and C that are more than 0. Here I have given them as 1, 1 and 1. So it's equilateral. So expected output will be 3. But there is nothing that prevents you from giving 1, 1, 2, 1, 2, 3, in which case the expected output could be the respective value for the tryout. Now lines 22, 24 and 29. 22 checks for S1 equal to S2. So you give side 1, side 2 to be equal. Here we have given all 3 sides to be equal, which is okay, which is just slightly stronger than 2 sides being equal. Expected output EO is 3 because it's an equilateral triangle. Line 29 checks for scalene triangle, all 3 sides, invalid triangle, where the sum of 2 sides is less than or equal to third side for something. So I have given inputs as 1, 2 and 3, expected output is not a valid triangle 4. If I give 2, 3 and 4, then it becomes scalene triangle, expected output is 1. So like this I can give test cases. If you give these predicates that you find here to what we call a SAT solver or an SMT solver, then that solver will give you the test cases back automatically. But for small examples like this, we could just look at the predicate and assign values to the 3 sides such that we get the desired value that satisfies the predicate. That is, it makes it true once and it makes it false once, and we set the expected output to be based on how the program works. So this is how the test cases for predicate coverage, for the predicate being true and the predicate being false, will look like. Now for clause coverage, this is just again a small sample. You could do it similarly for other predicates also. I have given it for the predicate in line 18 and again for the predicate in line 29. All other predicates you can do the same thing. It's just that it gets too cumbersome to write it, so I have not written it. So for the predicate in line 18 had 3 clauses. First one was S1 less than or equal to 0. Second one was S2 less than or equal to 0. Third one was S3 less than or equal to 0. So I have given some test case values, inputs for A, B and C, what the expected output is. Clause coverage being true, clause coverage being false, per clause at a time. So those are the rows. Similarly, for the predicate in line 29, there were 3 clauses, S1 plus S2 less than or equal to S3, S2 plus S3 less than or equal to S1 and so on. And these are the 3 values. You could give any value that satisfies this condition for each clause being true, each clause being false, and set the expected output to be whatever the triangle type turns out to be. Now, I have not given out the working for CACC. So basically you take this predicate, it has 3 clauses, you can make one clause active at a time, first clause, second clause, third clause. You have to see what are the conditions under which that clause determines the predicate, then take the truth table and write out the test cases. If you remember, we'd seen that last week. I have not worked that out here. I request you to try it out once. What I have given in this slide is for this predicate in line 18, if you do correlated active clause coverage for clause A, first clause, that is S1 less than or equal to 0 being a major clause. So that is given in capital T, capital F here. Means I am considering it in the 3 clauses, these 3 clauses, I am considering the first one to be the major clause. And you can go on like that and give some values A, B and C and expected output. Similarly, you could take the predicate in line 29 and do the 3 clauses and take each clause takes turn to be a major clause, and then what are the values, what is the expected output. You can write test cases for CACC for other predicates also. Please do try it out at least for one more so that it acts as a good practice for you. So this was it for the example. Basically, the points that you have to remember moving forward is that when we look at source code and when we look at decision statements in source code, the predicates that label the decision statements could be in terms of inputs variables, in which case the test cases can be obtained easily, or it could be in terms of internal variables, local variables, in which case you have to rewrite the internal variables in terms of inputs and ensure that you also capture any conditions that might be needed to reach the predicate. So you have to make sure that the predicate is reachable, rewrite any internal variables that you find in the predicate in terms of inputs, and then you get a logical expression that is ready for testing. On this logical expression, logical predicate, you could apply any of the coverage criteria that we saw. In this sample, we did predicate coverage, clause coverage and CACC, which are 3 useful logical coverage criteria. Work out for CACC how a clause determines a predicate and then write your test cases. For small examples, you could manually look at the clauses and write the test cases. For larger examples, you might have to resort to a SAT solver or an SMT solver. I'll give you an overview of SAT solvers at the end of this week's lectures, which will help you to get started with at least understanding how to use SAT solvers. So these were 2 simple examples that we saw on how to apply logical coverage criteria for testing the predicates that occur in source code in a method. Moving on, we'll see one example of specification and one example of a design document. I'll stop here for this lecture. Thank you.